one was discovered as late as a year back, a year and a few months back. And that is the largest known prime number. It is also the largest known seen prime. So at the Guinness Book of World Records, you'll find that over the years, the largest known primes happen to be of that class from that particular set. There's a star in 51 and 52. That basically means that we don't know if the 51st one is the 51 written there. But we do know that up to 50, those are actually the first 50. In other words, there's a possibility there's another one or two between 50 and 51, but we don't know that. It's only recently that we've discovered that the first 50 are the first 50. In fact, there was a star against many more than this, till let's say about a year back or something like that. This is the largest known prime number. As you can see, it has over 41 million digits, decimal digits. And there is the GIMPS project, where you will get all this data from which I've picked this up. There is more data on primes up to a particular point, up to x, and you can see a table of x which basically goes through powers of 10. And then there is the second column, which is the list of the number of primes up to x. And the third one is a guess as to how fast that function grows. And that guess is that we're looking at some function that looks like x by log x. Now, it's a very strange function that somebody should think of when we want to compute pi x. And it was the 19-year-old Gauss who looked at data that was given to him, probably not as big as this, because in the age of non-computers, people computed by hand. And you can imagine that he didn't have this kind of data to look at. But with the limited data that he had, he probably plotted some graphs and so on. And he came up with this function that closely approximated pi x. That function was x over log x, which means it's slightly smaller than x, but only slightly. You can liken it to x to the power of 1 minus a bit. That is what x by log x looks like, because log x is a very small power of x. So if you look at that and look at the last column, that is the column that compares pi x to x by log x. And you can see that the ratio is not so far from 1. Okay, so Gauss conjectured at that age that the correct answer is 1, that the limit of pi x to x by log x is actually equal to 1. So there's Gauss and also Legendre, who pronounced the same thing, a little bit about the same time also, maybe a little earlier. But it's mostly Gauss because I think he was 19 years old, so people give him more credit for guessing this. So this is the big result. Well, this is leading up to the big result. There's a picture of Chebyshev, which says that if you look at the limit of pi x to x by log x, that limit, if it exists, is 1. If it exists. He was not able to prove that it's equal to 1. So what he basically proved was that this ratio is between 1 minus something and 1 plus something. Now, that doesn't prove the limit exists. So he was able to prove that if the limit existed, it was 1. This is 1850s. And then something happened about 50 years later. And probably the biggest result in number theory till that point in time came about. This is called the prime number theorem. This tells you that the ratio of pi x to x by log x is 1. So in the limit as x goes to infinity, the ratio of that is exactly equal to 1. And this is the contribution of 4 people, well, 2 people at this time, 1896. It also says, by the way, that if you want to look at the nth prime, you just have to multiply n by log n, and you're approximately there. So those 2 statements are equivalent statements. So this is a picture of the 2 mathematicians who actually proved this. And they proved this by using tools from complex analysis. Nothing really to do with number theory. And that was the start of understanding that to do number theory, you have to borrow from other parts of mathematics. So already we had module theory coming in about 10 years before this, ring theory coming in, and then complex analysis, more specifically because of function. So these are two guys who independently proved this the same year. So the credit for proving the prime number theorem goes to these two gentlemen, both of whom coincidentally lived to be almost 100. Okay. Now that's not a precondition to prove the prime number theorem, of course. But here is another pair of mathematicians. I'm sticking my neck out when I say this because honestly, officially, the credit to prove the prime number theorem without using complex analysis goes only to Selberg. But mathematicians believe it was actually joint work with Erdős that got Selberg ticking. I'm not going to go and tell you the story that we believe is true. There is no proof that that story is true, but that's what we believe, because both Selberg and Erdős are people who died not so long back. So there's any number of people who knew them intimately. But when the story of the contentious proof came about, then there would be tight-lipped. They wouldn't talk about it because it soured the relationship. I will not say any more than that. I'll simply leave it at that. But this is about 50 years after the initial proof. So what is great about this proof is that it did not use complex analysis. It used directly only basic number theory. It's also much harder to understand because of that. So the moral of the story is, if you're not willing to use tools that are provided to you, then you pay a price. You have to go circuitously. All right. Now I need to start looking at the time. I think I should be okay telling you a little bit about this, but only a little bit. So this is about primes in arithmetic progression. This is an old result from Dirichlet, 150, almost 200 years old, which says that if you take any arithmetic progression whatsoever, so an arithmetic progression is something that has a first term and has a common difference. So if the first term and the common difference are co-prime, which is obviously necessary, because if they're not co-prime, whatever divides both of them will divide all terms in the sequence. So for example, if you take 10x plus 15 and vary the x, then 5 will divide every term there. So you basically need the common difference and the first term to be co-prime for you to have a chance to prove that that sequence has infinitely many primes. This is what Dirichlet proved. Complicated mathematics, by those days standards, now we teach this in our standard first course in analytic number theory. There's a little more technical detail there, more than I told you, but let's forget what that phi d is that you're dividing by and what that pi a is. This is a picture of Dirichlet. One of my favorite results on prime numbers. There are probably more unsolved problems on prime numbers than there are solved. Amongst the solved ones, I picked the prime number theorem, and I picked this. Chebyshev, the same guy who almost proved prime number theorem, said there's always a prime between n and 2n. It was not enunciated by him. He was the first one who proved it. But we don't follow his proof anymore. It is a lot more complicated. Now we have a proof which is much simpler to understand. The first simplified proof of this, Chebyshev is 1850, came about 1915. Ramanujan published this in an Indian journal, and that got noticed. Very short and cute proof. And that got upped to an even simpler proof given by a 15-year-old mathematician called Paul Erdős. You'll see more and more of Erdős here. I'm going to jump through these slides. There's about 5 or 6 slides. This is about coloring. It's what is called Van der Waerden's theorem, and it's a part of combinatorics, but it has links with number theory. Whatever happens after this is all number theory. This in itself is more combinatorics. So what it says is, if you imagine coloring all the integers, positive integers, in finitely many colors, let's say you have 3 colors to color it with, and you give me a number, whatever number you give me, like 10 to the power of 10, large number. No matter how you color these integers in 3 colors, there will be some color class in which there is an arithmetic progression with 10 to the power of 10 consecutive numbers, all colored red or all colored blue or all colored green. And this has nothing to do with the number of colors being 3. So you can tell me your favorite number of colors you want to choose. You can tell me your favorite number as large as you please. And I will tell you that no matter how you color all the integers in that many colors, there'll be some color in which there's an arithmetic progression with that many consecutive of Van der Waerden. This is a theorem. Van der Waerden, by the way, is very well known for his book in algebra. So when I was an undergraduate, in fact, our college library had the volume 1 and volume 2 of basic algebra by Van der Waerden. The style of writing in those days is gone out of favor. Now if you follow a book like that, you'll get lost because notations have changed. But Van der Waerden was essentially an algebraist. The only result he did in combinatorics was the theorem that is named after him, and then he went back to algebra. Never produced anything in combinatorics or number theory. This is Erdős and Turan theorem, conjecture. I'm going to skip all of this because I think this will be a little harder to go through. This is more along the same lines towards proving the theorem of somebody who's alive. He's one of the few people on the slide who are actually alive. Okay. So these are young people who proved a very well-known result. Green and Tao. Tao is one of the most famous mathematicians alive. Now both these guys are about 50 years old. I'll get to say a little bit about the twin prime conjecture. So what are twin primes? These are primes that differ by 2. So what is the twin prime conjecture? It basically says there's infinitely many pairs of primes that differ by exactly 2. So you begin with 3 and 5, and you follow that up with 5 and 7, and then 11 and 13, and then 17 and 19, and so on. So at the initial stage, there's a whole lot of primes that differ by 2. But they thin out as you go up. And the conjecture, a very, very, very famous conjecture about prime numbers, is there's infinitely many such. This is the twin prime conjecture. I'm going to skip this conjecture of Hardy and Littlewood from 100 years back. There is Hardy and there's Littlewood. I'm going to skip this theorem of Brun. And I'm going to skip this conjecture of Polignac. I'm going to tell you something more recent. This tells you a little bit about what has been done in the recent past because we made some inroads to the twin prime conjecture. And so this very obscure, unknown mathematician called Yitang Zhang, who was about 60 odd, proved this result, and it came from nowhere. Usually when big results come, they come from big people, known people. Yitang Zhang was not in anybody's roadmap. He was not a very famous guy till that point in time. But people stood up and took notice because he proved this seemingly obscure result, which says this, that there's some number n, less than 70 million. It's a very large number. So that for that n, there's infinitely many pairs of primes that differ by that specific n. Now remember, the goal is to prove n is equal to 2. But what Yitang Zhang says is that some number, not more than 70 million, less than 70 million, has the property that there's infinitely many primes that differ by exactly that n. Infinitely many. So Yitang Zhang's results got extended because the moment somebody noticed this result, the hundreds of people started working on it. Terence Tao started a polymath, a group on the net which anybody could access. And it was a collaborative effort. The idea was to get the whole world interested. A lot of research on this, a lot of good research, maybe this coming up. This is the 39-year-old Riemann, or maybe a little bit less than that, died at 39. I don't want to get. So I will close with a picture of Riemann and a few selected bibliography items, books as well as articles, but very, very good. Not enough to cover all things that I said in the slide. But I have Yitang Zhang. Comes right at the end, as I said. And that's it. Thank you for your patience. I know what to use this. Do you have any questions to ask?
Yeah.
I hadn't expected any questions. And normally when this happens in the class, we practitioners of teaching, we've been teaching for a very
very long time, we believe that the students understood everything. That's why they don't have questions. Because that's what we like to believe. It's not true. That usually happens because you're least interested in what I'm talking about. Or if you're interested, you didn't understand. If you don't understand anything, then you obviously don't have any questions to ask. I can tell you that from first-hand experience of sitting in the audience for such a long time. So when that happens, then obviously questions don't come. And somebody on the other side, like me just now, would like to believe this was crystal clear, you understood all of it, you enjoyed the lecture, there are some claps and so on and so forth, but that's all misleading. That's not true. But still, it would be nice if somebody who asked you the first question, because you know what happens? Once the first question comes, then suddenly there is a sequence of questions. It's always difficult to make the first move. Yes. Please wait. Yes. All questions are so a conjecture is a guess that one makes based on some evidence in mathematics. Usually, when the question is made by somebody very well known,